My name is Caroline Walker, and I'm speaking today about principal component analysis. So just to provide a brief overview of where we'll be headed in this talk, we're going to spend most of this session focusing on a very small dimensional data set. In fact, a data set with just 2 features, which is quite different from the type of data set that you'd probably be executing PCA on in real life, right? You're going to be in a machine learning context working with a data set with many, many features. The problem is that data sets such as that don't lend themselves well to visualization. And our goal is to build a mental model of what happens when PCA is executed. So our hope is that by focusing on this small 2-dimensional feature space and being able to really visualize what's happening there, we'll deepen our understanding and our intuition about what's happening when we're executing PCA in much higher dimensions as we would be in practice. All right, so let's jump right in. First of all, very broadly speaking, what is principal component analysis? Well, first of all, it's a mouthful to say, so I'm going to refer to it throughout this talk as PCA. And it's a dimensionality reduction technique. So it's one of many dimensionality reduction techniques that are available. But just broadly speaking, when we're thinking about dimensionality reduction, we're imagining starting out with a feature space with tons of features, right? I put 10 up here for as an example because that's all I can fit on my screen. But in reality, we could have 100 or more. And for any number of reasons, we don't want to start building a model off of 100 features. We want to reduce that, distill the information in those 100 features down into something that it could be advantageous to start with. So we're taking a large data set, or a large feature space, we're reducing it to a smaller number of features, and it's important to keep in mind we're talking feature extraction here. So we're not just throwing out some features and keeping some others. We're changing the features we have to arrive at a new set of features that we believe will be more informative to build a model off of. And when we're using principal component analysis to find those new features, the name of those features are principal components. Okay, so that's very big picture principal components. And dimensionality reduction in general. Let's take a look at some of the specifics, the things that differentiate PCA. So when we use PCA to find a new feature set to build our model with, the new features we obtain are going to be linear transformations of the original features. Those are the only options that we're exploring with this method. When we find those features, they're going to be linearly uncorrelated with each other. And here's the really big one, kind of the driving motivation in PCA. We're looking for a feature set that will retain maximum variance from the original feature set. So if we think really big here, say we started with a feature set with 100 features and we reduced it down to just 10 using PCA, well, PCA promises that that set of 10 new features captures the maximum variance from the original feature set that can be captured in just 10 dimensions. All right, so there we go, maximum variance, big idea to take away from that overview. Now let's take a look at this very small dimensional data set I promised you. So here it is on the screen, just 6 data points and 2 features. We're calling them feature 1 and feature 2. Looking at that data plotted in 2 dimensions, we can already see there's some linear correlation there, which is an indication that there's redundancy. The information contained by feature 1 is replicated somewhat in the information contained in feature 2, and so we feel hopeful that we can achieve good results by reducing the dimensionality here, by finding a single feature which can adequately summarize what's happening in 2 dimensions. So because variance is so central to this idea of PCA, it's worth taking a moment here to notice the variance that's present in our original data. So feature 1 has variance just about 1.5. Feature 2 has variance 0.7. So altogether, we're talking about a variance in our feature set of 2.184. That's kind of going to be our benchmark moving forward. We're trying to capture as much of that variance as possible in a single dimension. So when we think about trying to reduce the dimensionality of this feature space via PCA, we can visualize any new feature that PCA would create as a line in this 2-dimensional feature space. So let's put one up there just to start with. So I've labeled it line A, and this will represent a new feature we're considering. Let's call it feature A. So we can see the values that our data points would take in terms of feature A by projecting those data points onto the line and looking at the values they yield. And what we're hoping for, we want to retain maximum variance. We're hoping to see very dispersed data points. Those blue dots, we'd like them to be very greatly spread apart. That's not really what we're seeing here. And in particular, let's take a look at these 2 points that I've highlighted in yellow. When we think about those 2 points in the feature space F1, F2, those are very different points, right? They're capturing very different information. However, when they're transformed into feature A, they're taking nearly identical values. So that's a good indication off the bat that maybe we don't feel so warm and fuzzy about feature A. We may be losing a lot of information here. And we can quantify that mathematically by looking at the distribution of the data points in feature A, right? Measuring their distance from the origin along line A. And we can calculate the variance, and it's 0.328. So that's not just like a little bad, that's pretty much horrible, right? If we look back at the variance that each of our original features had, and remember our big picture goal was to take this from a feature set with 2 features to a feature set with 1 feature. Well, we could have done better to just throw out feature 2 and keep feature 1, right? Feature 1 has higher variance than feature A. If we want to think about it in terms of percent of the variance retained, feature A is capturing just 15% of the variance that was present in our original data set. So we can cross feature A off the candidate list. This isn't the direction we want to go. Let's look for a better feature. So put a new line up here, labeled B, representing feature B. And just off the bat, taking a look at this line, we can see this is a pretty nice trend line for our data. Our gut may be telling us we're going to get better results here. Looking at the projection of those data points onto the line, we can see that they indeed are more widely dispersed than we saw with feature A. We can calculate the variance. Comes out around 1.9, which is a big improvement over feature A. And as a percent of our overall variance, it's 86%. So that's great. You know, here we would choose feature B over either feature 1 or feature 2. Feature B alone is capturing more variance than either of those original features did independently. But the question remains, is this the best we can do? Is this the feature that captures the most variance possible for our data? So PCA is the method that provides the solution to that problem. When we follow the steps of PCA, we're using a method that has been mathematically proven to find the new feature set that captures maximum variance. So what we'll do next is talk through the steps of PCA, and then we'll apply it to this example data set and look at the results it yields. Here we go. So I'm going to put 4 steps up here summarizing how PCA is executed. But it's really important to keep in mind that when you're doing PCA or using this method on your data, you're not executing these steps one by one in order, right? It's happening behind the scenes in whatever implementation you're using. So if you're working in SAS 9, you're going to be using proc printcomp. If you're working in SAS Via, you're going to be using proc PCA, or maybe you're using SAS visual data mining and machine learning, in which case you're going to be setting all your parameters in the user interface there. These are the steps that are happening behind the scenes, and each of those methods offers you information about these various steps. We want to really know what's going on. So here are the steps. So the first step is we're going to calculate the covariance matrix of the original feature set. And I've started the word covariance there because there's a number of situations where the correlation matrix is actually preferable. And any implementation that I mentioned where you could be using this gives you the option of choosing between the correlation or the covariance matrix. For our purposes in the example we're looking at, we'll illustrate use of the covariance matrix. So once you've got that matrix, you're going to calculate the eigenvectors and eigenvalues of the matrix. And you're going to order them from largest to smallest according to the magnitude of the eigenvalues. And the notational convention here is to call the largest eigenvalue lambda 1, and the eigenvector associated with it we'll refer to as V1. And that eigenvector V1 is really the star of the show, because here in step 4, eigenvector V1 is going to show the direction of maximum variance within the data set. So that's the very direction we're looking for. If we put our new feature line spanning that vector, we will capture maximum variance. So before we apply these steps to our data, let's just take a moment to think about them a little more deeply, further develop our mental model of these steps. So now I'm showing on the screen 3 different data sets with far more data points than our 2-dimensional example we're looking at, but still data sets in just 2 dimensions, right? The feature space F1 and F2. And here we have enough data points in each data set to really begin to see the shape of the data cloud there. And we have 3 very differently shaped data clouds. And now I'm going to superimpose upon each of those plots the covariance matrix. And when we think about what the covariance matrix is doing, it's capturing important information about the shape of the data cloud. It's not complete information, but it's telling us the things we need to know. For example, the direction of maximum stretch of that data cloud. Because you can see in each 3 examples, those data clouds are stretched kind of in different ways. So now I'm going to superimpose over those data clouds the eigenvectors we were just talking about. There they are. And in green, there's the one we're really interested in, the eigenvector 1, right? That's the eigenvector with largest eigenvalue. And we can see that it indeed is pointing in what appear to be excellent trendline directions, those directions of biggest stretch. We've got the second eigenvector, V2, in each of these plots as well, and those are almost very difficult to see because they're so short. And that's because in this plot, I've followed the convention that's commonly used when we're visualizing eigenvectors in PCA. I've plotted the lengths of these vectors to reflect the magnitude of the eigenvalues. So you can see those second eigenvectors had very small eigenvalues. They're very short vectors. Just to get a better look at them, I've plotted them here as unit vectors so we can see that orthogonality that PCA also promises us. All right, so now let's return to our example data set and apply those steps we just talked about. So here I've shown our covariance matrix. From there, we can calculate the eigenvectors and eigenvalues. And over on the left is the eigenvector we're interested in, V1, and its eigenvalue. So let's plot that in our data space. You can see V1 looking like a great trend line, and we'll draw the line that spans it, representing our new feature we're considering, and we'll call this new feature principal component 1. And we can see that it is an excellent trend line for our data. In fact, 3 of our data points are falling right on that trend line. Let's see how they all fall as we draw our projections. Look at the dispersion. They're quite dispersed. We can calculate the variance. We can see we're achieving variance of 2.038. So as a percent of our overall variance, it's 93%. And because we used PCA, we know that this is the optimal solution. This is the most variance that can possibly be captured from this data set in a single new feature. All right, before we move on from here, I just want to take a moment and focus a little bit more on one number on the screen. That's that variance number, 2.038. We've seen that number before. Let's take a look at where. Back when we were talking about the eigenvectors. So 2.038 was the value of lambda 1, the eigenvalue associated with that first eigenvector. And this is not a coincidence. This is in fact always true in PCA. And this becomes extremely helpful when we move from thinking about this PCA where we're reducing a 2-dimensional data set to a 1-dimensional, 1-feature data set. Let's go back to that example where we had a feature set with 100 features and we want to use PCA. So now we can use the covariance matrix and the eigenvectors to find 100 principal components. But we have this added question of how many of those do we want to keep in our final model? Probably not all 100, because then we haven't really reduced the dimensionality. But do we keep 80 of them? Do we keep 50? Do we keep 5? How do we gauge how many we want to keep? Well, these eigenvalues provide the key there in making that decision, because each eigenvalue will tell you how much additional variance will be retained when the principal component associated with that eigenvalue is kept in the model. So just to delve a little deeper in that, I put together a dummy data set or an example data set with 10 features in it. And we can take a look at how the process would go of looking at those eigenvalues and deciding how many to keep. So here's my example feature set of 10 features. Principal component analysis was applied. It yielded initially 10 principal components, and we need to decide how many to keep to move into the model building phase. So here's a visualization of those 10 principal components, and each one is going to have associated with it an eigenvalue. And remember, PC1 and lambda1 is going to be that largest eigenvalue, and they're going to decrease in value as we move down the list in size. Okay, so let's take a look. For this particular example data set I put together, it's probably useful to know that the total data set had variance 58. And here we can see that the first principal component has variance 38. So we're capturing in just one dimension 66% of the variance that we originally had summarized over 10 dimensions. So that's pretty great, right? Let's see how that improves when we add the second principal component to the model. So in this example data set, the second principal component has eigenvalue 9. So put together, if we built a model off of just these two principal components, well, we would be using a feature set that had 81% of the variance of our original feature set. And we can keep going, add in that third. You can notice here, we're seeing a pretty steep drop in the magnitude of the eigenvalues as we go through this data set. And that is pretty typical of many situations where principal component analysis is applied. Okay, so if we add principal component 3 to the model, now we're capturing 90% of the variance that was in our original data set, and we may decide that's a good stopping point. That's enough for us. We're pleased to be able to use just 3 features for model building. So we decide to throw out all the others. It's just not worth it to add a whole nother dimension to add, say, just 2.5 variance units captured. Okay, so we visualize this here. If you're implementing PCA in SAS visual data mining and machine learning, it's going to produce a number of nice graphics for you to help explain the choices made about which principal components were retained. So I want to take a minute and look at those graphics as generated from this same example data set here with 10 features. So the first one you're going to get is this. So along our horizontal axis, we just have the principal components from first to last, 1 to 10. Our vertical axis is showing us the magnitude of the eigenvalues. And what's really interesting here, what we're looking for in a graph like this, is sharp elbows in that plot, points where we're really seeing deeply diminished returns from adding additional components to the model. It's just showing us that extra feature is probably not worth adding. The second diagnostic we can look at here, I really like this one. We've again got principal components along the horizontal axis, but now the vertical axis is showing us the cumulative proportional eigenvalue, or a nice way to think about that is showing us the proportion of variance that will be captured based on the number of principal components you include. And you can see that when this model was run, I'd specified we'll keep as many principal components as necessary to retain 90% of the original variance. So that's where that number of PCs selected line is coming in. All right, so one more topic I want to touch on before we wrap up here, and that's the idea of reconstruction error. Because we've talked about the benefits, right, how PCA can be used to reduce the dimensionality of our data set, but there's a flip side to that, which is that we could potentially have information loss, and we want to have a way to visualize and measure that. So here again, I've got our original two-dimensional data set up there. That's what we started with in the 2D feature space of feature 1, feature 2. And we turned it into this, right, a single feature, principal component 1. So now we want to flip that around. We want to say, let's start with the data values of principal component 1 and try to reconstruct our original data values in the F1, F2 space. And of course, we don't get our actual original data values back. We get an approximation. We're going to get all points falling on that line, PC1. So now let's superimpose. Let's look at both those plotted at once. And we can see, right, our original data points and our reconstructed data points. And when we think about reconstruction error, what we're interested in is the distance between our original data points and our reconstructed data points. So that's visualized with those dotted lines. And those lines should look very familiar, right? Those are the same lines we saw when we were projecting our original data points onto the new feature line. But now we're thinking about the length of those lines, or the distance between the points, as representing how much information we may have lost when we reduce the dimensionality of our data set. And we want to measure that mathematically. What we do is we square all those distances and average it over the whole data set, and that's referred to as the reconstruction error. And our hope is that if those distances are small, it's quite plausible to think, well, it wasn't really information that was lost, it was noise, right? We've actually removed some noise from our data and perhaps are creating a new feature set that will better enable us to build a better model. But if that reconstruction error becomes very large, well, that isn't quite so plausible anymore, and we might become concerned that we've really lost something that could have benefited our model. Well, the good news of PCA is, through some lovely mathematical symmetry, the goal of minimizing reconstruction error is actually equivalent to maximizing variance retained. So in finding the feature set that retained maximum variance, we also found the feature set that minimizes reconstruction error. All right, so in closing, just to revisit some of the main ideas from our talk here, PCA is a dimensionality reduction technique. The main goal of PCA is to find the new feature set which retains maximum variance, and that's equivalent to minimizing the reconstruction error. And we have these other constraints, right? The new features found are linear transformations of the original features, and they're going to be linearly uncorrelated. All right, well, I hope this talk was informative and maybe enjoyable. If this has whet your appetite to learn more about principal component analysis, then I highly recommend the Springer text by Jolliffe. It takes a very deep dive into many aspects of PCA, which we obviously couldn't touch on in a 20-minute talk. If you're looking for a shorter read, but something very mathematically rigorous, I highly recommend these next two articles. They come at PCA from slightly different perspectives, but they both have beautiful derivations of the linear algebra proofs for why PCA provides optimal results, as well as very interesting discussion on the topic. And if you're just looking for a little more fun, I recommend this fourth link. This is an interactive visualization of PCA in both 2 dimensions and 3 dimensions. So spending some time playing around with that can further develop that mental model of the process. All right, well, thank you so much for listening. Have a good day.